sorry. I'm like kind of just testing this restream thing to see if it works. It looks like it thinks it's working, but YouTube doesn't seem to work. Only Twitch. Why is that?
She sings la pâté, chérie.
It's not la pâté, la pâté.
Like a pâté.
It's not.
But for the doggies and the kitties.
It's not that at all.
It's la pâté.
No.
La pâté.
Oh, it is working on YouTube.
On aime bien la pâté. Ah putain, je vais mourir.
Just not.
Moi, j'aime pas la pâté.
The sound is really low.
Moi, j'aime pas la pâté.
I think that's because I'm talking really low. Hello, how are you?
Ah putain. Hi.
I'm trying. Hi. I'm trying a new service called Restream to make it a little bit better.
Ça m'a pas manqué de faire Valdorm avec des pouces.
The sound is really low, so I wonder if I can chat overlay. Let's see how this works. Copy this URL into OBS Studio. Alright, so I guess I can copy this URL. Let me try this. I'm so sorry that you guys are kind of like guinea pigs right now. I'll call this Restream. Here's the URL.
C'est pas ATM, c'est comment ça s'appelle?
But it's kind of ugly. God, that's ugly as hell.
Ça ressemblait quand même pas mal, hein?
Chat is ready to display messages, but it's not showing any other messages, right? Oh, I think it's pointing to the wrong one. What the hell? So how are you guys doing? Maybe this isn't the right URL. No, it is. It's the right URL.
Ah, shit!
Preview settings default top. Oh, here it is. I can change the opacity. Oh, background opacity. Chat background opacity. Chat message opacity. Got it. Scale 100. Hide messages. Alright, I think I got it now.
Mange un fruit.
Alright, I think that's better.
Mange un fruit!
That's my partner talking over there. It's still quite low, really. Let me make sure my mic's pointing at the right thing here. Yeah, it's the right thing. And I have it like, maybe I can just speak closer to it. Is this better?
Elle a fait un GG move.
But why am I not seeing the new chat messages here? It says display ready, and then it doesn't show the new messages.
I'm not staying
God
for
damn
that
it.
shit. Turns out to fall in a poison.
None of this. I just wanted to fix chat. That's kind of the reason why. Oh, there it goes. Hello. So it kind of is working, right? It puts it on top. Is that how it normally is?
Les fruits, putain.
No, it's working. All right, cool. Let's get started then. I had a really long day today, so like I didn't want to like pass the day without doing any streaming because like I mean I like you guys, but also I want to learn stuff. It drives me a little bit crazy. The TISM really wants me to keep to a routine. So I want to do a little bit, you know? So today won't be a great session in terms of going deep. yesterday we worked on an Elixir Discord bot, and that's cool and all, but that takes a lot of effort. So I was kind of thinking to do like
Le PC,
Atari
à la
stuff,
limite.
Atari 6502, at
Ouais,
least
les
review what we've learned so far in
Mais c'est pas
Atari
plus chiant.
6502 assembly programming. What do you do for the day job? I don't have a day job. I often do like freelance work for like sort of like contracting for programming and stuff like that. Sometimes programming, sometimes like product
Tiens, je vois pas
definition.
trop
What do you
le-
call it? Like when you own and define the
Tu
product.
l'as eu?
Yeah, it's a little late for streaming. Wow.
Sympa.
I wanted to try it. I was out all day. And then what was I saying? Oh yeah, I do product definition work, like product manager, product owner. I do like tech work where I program stuff or architect stuff or like help manage technology folks or do some research stuff. So that's kind of what I do. Often in startups, sometimes in really large companies. The chat messages look a little like
J'ai dit pourquoi
transparent, right? That's a little annoying.
pas. J'ai dit pourquoi pas.
So maybe I should change the message opacity to like something like this. Oh, does it change it automatically? Here, let me try this.
Ce que tu veux.
I don't think so. I don't think it changes it automatically. I think I have to change the URL. Although I think the URL doesn't really change anything. That's kind of weird. Properties. He has the same URL, so it doesn't change anything.
Oui, bah je m'attends à des gens un peu plus expérimentés en niveau 100 quand même.
Anyway,
Allez les pambas.
so I'm thinking we do. Thanks, Kingo. I think we're gonna do Atari stuff to review. Let's review first. Maybe we won't even get to the new stuff. Let's see what happens.
Je crois que j'ai
So
rien.
we'll go into Atari. Here's our Atari stuff.
Ah bon?
We have our browser here.
Tant pis pour vous. C'est un scandalo, bro.
All right. So when we do Atari stuff, we basically have our thing we're reading,
Immense ce
which
pampa.
is here. Let me cut this a little
T'as vu
bit
la
too.
taille du pampa?
Which is Atari Roots. We're reading this book, Atari Roots, that's teaching us both about 6502 assembly language and also we're learning about the Atari in general because, like, I never had an Atari, and like a lot of the problems I've had so far on this is more about like how do I format a disk in Atari? How do I don't know, save a program or load something? Like, the book doesn't expect you to be like a total Atari noob, but that's exactly what I am. But hopefully we're getting a little bit better. So there's this book, and then we also have this Altera Atari emulator. That's the thing on the right here that we can program. And we are kind of emulating an Atari 800 XL. And we are using the Mac 65 assembler with the Bug 65 debugger for, you know, running and debugging assembly programs. So that's what we're doing, and we're gonna use the PDF version of this book to read. Where is that? That's over here. And we were kind of far along. I think we're on page like 89 or something like that. Yeah, we learned how to basically auto run a program. I think we did all of this, right? Writing programs that will run when loaded. Let's see if we can actually do this real quick, right? I'll try to remember how this works. Let me make this a little bit bigger. That's good, right?
Il y a tout qui rentre,
You're
il y a
learning
rien
it
qui
just for
sort,
fun?
ok?
Yeah, just for fun. Never had an Atari. I never used an Atari, but like I have this weird like fascination with old retro machines. You hear about all these like how programmers got started. They got started like making
Mais
games in
qu'est-ce
their
que je voulais dire?
bedrooms, you
Il n'y a
know,
pas eu
on
un petit
8-bit
truc
machines, and you're
derrière
like,
ta...
wow, like that had like less than 48K of memory, and now we have like gigs of memory, and I still run out of memory. I was doing Advent of Code, and I was like running out of memory. It's like, can you imagine if you had to program these old machines? Anyway, it sounds kind of cute and nostalgic in a way that I never knew it. So I just want to kind of play with it and see about it, I guess. So let's see what we can remember because I don't do this every day. So let's see how this goes, right? The first thing we do is I think we can run our Max65 assembler. And that's Max65420 is the one that we've been using. And in here now we have the program. I think if list you see that the program is empty. God, should I try to remember like our 2+2 program off the top of my head? Let's try it. 100. We first tell it that we want to put this program in memory. I think that's opt-obj, isn't it? Let's try it. Okay, and then the next thing we want to do is give it another directive that tells it to put the memory into 0600. That's page 6 of the memory, and that you just have to kind of know where in memory you're going to put the stuff. I don't know. I think the next chapter is actually how to pick the right memory addresses. So right now they just told us to use this. And then after this, I think we clear. I think we create a label, add numbers. So this is a label. Notice that it's like one space before the rest of the commands. That means it's a label. Spacing like matters in this stuff. And then this is the beginning of a label, so it's kind of like a way to refer to this subroutine later. You can be like go to or jump here. And then we want to do clear, no, not clear carry. We want to do like clear decimal mode or something like that, which is like there's two modes for the Atari to do math, and one is binary and the other one is decimal. And so far we haven't learned decimal, but we know we don't want it. It breaks things. So that's the CLD opcode. And then we want to tell it to clear carry. This is the carry flag in the 6502 CPU. And it's saying like, in case you do any overflow, because the largest number is what? It's 8 bits, right? So the first bit is 1. The next bit is 2. Then it's 4, 8, 16, 32. And then if they're all on, that would be, wait, no, the largest number has to be 256. What am I doing wrong? It's 8 bits. Oh, that's different, right? So 8 bits, where's my hands? Here they are. So this is like 1. The first bit is a 1. Then it is a 2. So if they're both down, it's 3, right? Yeah. 1, 2, 4, 8, 16, 32, 64, 128. So if this bit was on, it's 128. But if they're all on, the next one would be 128 would be 256. But it's 1 less than that, so it's 255. So the largest number that an 8-bit computer can do is 255. And so if you want numbers bigger than that, you have to keep track of the carry flag. So we're clearing it in case it was already set. And then the next thing we do here, if anyone wants to try to remember, go ahead and type it if you were here for the previous videos. Now I think we want to load into the accumulator the number we're adding. So let's load into accumulator the hash symbol means that it's we're using a direct, we're talking about a real number, not a memory address. So we're putting the number 2 into the accumulator. Then we are going to add with carry, I think, and we'll add something to it. We'll add, let's say we add the number 10 to it, right? Let's see if this works. And then after that, inside of the accumulator should be the number 12. And then we're going to take that number and put it into another memory address. We've been using hexadecimal address CB. So we're storing accumulator into memory address CB. And then after this, we're going to return from subroutine. That just means like we're done with add numbers, the 120 where we had add subroutines. And then we're going to tell it we're done. So we do a .end. That's a directive to the assembler. So let's list this now. Does that look kind of right? Does anyone see anything wrong with this? Now you compile it by typing ASM. It seems to be fine with it. These are the hexadecimal codes for our opcodes. This is like this is the put it in the accumulator number 2, and this is the add with carry, and this is the number 10 in hexadecimal, and then here we're doing a store into memory address CB, right? Oh, here it is. It's all in here. So let's just see if, and then what we have to do is we have to store this onto disk, right? And that is called list. And then we can put it like, I think it's D1 is how you write it. And we'll call this like memory mem test. I think it's long enough. I forget how long these things can be. And we do dot source. So you see, well, this means it should have saved it to disk. And now what we can do is, I think we go to, it's probably CP, which is command processor. That takes us back to DOS. And now we can run the debugger, which is bug65. And you see memtest.source, right? That's our program right here. So we do bug65. This is going, now I think we can run our program by doing, first we can do display 0600. And you can see these are the opcodes for our program, D8, A9. This is the load accumulator with the number 2, and this is the 69 is the add with carry, and 0A is 10. So, and we can also display CB, which is where we're going to store our answer, and it's 0 right now. And then we do, we try to run it, and I think that's go 0600 space, and I forget if it's an @ sign. Is it an @ sign? I think it is. And you put the last number of the program, last address where the program stops. Okay, yeah, you see it right here on the browser. 0600 and 0608. Oh, I don't have chat on here. Let me add you guys back here. Alright, see you later, Kingo. Good night. Where are you, Restream? Here you are. Whoa, it's way...
Oh non, j'ai fait du caca. J'ai mis mes deux.
Hard to read. Alright, so it's kind of like the top thing is the last message. Alright, got it. So I can kind of probably just like do this for now. And I can put my thing first so it doesn't cut. There we go. That's probably good enough. All right. See you later, Kingo. Thanks so much for stopping by. Okay, so now we're going to try and run this. Let's hope this works. Hey, it worked. All right. So C is 12, right? Because A is 10, B is 11, C is 12 in hexadecimal. Why is my... Oh, I don't like this. There we go. I'm a little more centered now. So we've remembered how to write a very simple addition program and how to run it. And now we have to try to remember how to create an auto-starting disk, right? This is the hard part because this is a lot less intuitive for me. So let's see here. This is Atari DOS. To save a program using OSA, this is us. So this, let me check if I put this inside of our gist, because these kind of things are really helpful. Browser, where are you, browser? Here we go. Okay, so did we write down how to save a program? Here's debugger, Max65, bsave. This doesn't look like what it's saying here, right? To save an object code program using OSA, the correct form. Oh, this is OSA. And this is within Max65. Wow, that's really annoying. So here it is. So we should probably write this in here. We'll save this OSA. Where are you, OSA? This is save an object code program. Format is save, add numbers, just like whatever, and then the address that it starts at and the address that it ends. Okay, so we'll just put little stuff around this. And we will have this here now. Save, there we go. And we should be able to, I forget how to get back here. Is it just Q? Yeah, it's just Q. So let's try to save our version. We can do save. We'll do memtest.obj 06000608. And now we should see in here we have both memtest source and we have the object code. Alright, so we figured that out. Writing programs that will run when loaded. I've lost you guys. Oh, there you are. Okay. This is Atari. This is not us. This is the Atari assembler cartridge, not us. The init program, yeah, this is not us. Here we go. Running machine language programs using OSA Plus doesn't provide any init or load parameters to run. You just say run and then you give it the address. So we should be able to do run 0600 and that will run our program. Our program doesn't like output anything, so that's not useful. Oh, sorry, I wasn't showing the thing correctly. But anyway, I'm going to put that in our notes here. Save an object file. So we do run a machine language program. We just type run You give it the disk number. Oh, I guess that's showing that it gives you the disk number. Run 0600, and that will start at that address. Okay, cool. That's over here. We just was here, and then that's how you run it in OSA, and we're able to run it in the debugger also. Remember, this is kind of like not very helpful for us because unless we're in the debugger, we can't tell that it actually put the right things into memory. But you know, one test we can do that we haven't done is I'm going to press Shift F5, and now we're in cold. It's kind of like restarted the computer, right? And now I can do bug65, and now when I display CB, it's 0, right? So I quit out of here. I'm going to load the I wonder, so we learned how to save, but I'm guessing we can load. Let's go to the assembler max65 4200420. Now we're going to load, which is called enter. Enter %d1. What do we call it? Test memory dot source. File not found. Test. What do we call this thing? Mem test. Okay. So max65 420. I failed my mem test. So it was enter memtest.source. And now when I list it, I have the code in here, but I'm not running it, right? I still have to assemble it. So but it hasn't run. So which means you can see that it hasn't run because when I go to bug65 and I show CB, it's 0, right? And now when I quit this and I do run 0600, this did run it, right? So now when I go back into the debugger, bug65, and I display CB, you'll see that it has the number 12 in there now. So that's proof that it actually ran from the DOS prompt and not from the debugger, which is kind of cool, right? I mean, it's a little thing. Oh. Okay, so that was that review. Now we're going to try to figure out how we can write a self-booting program. Did I save that in the browser? Like how to... Yeah, we wrote down how to run it. Now we're going to write a self-booting program. All right, 2 ways to do it. We can use Atari's autorun.sys. But that one doesn't really work for us because we're not using Atari's system. We're using the OSA Plus operating system, which is still Atari, but I think it's like they continued to improve it afterwards. I don't know the history behind it all. So here we go. To use the OSA Plus startup utility, just boot OSA Plus and replace your master disk with a data disk with the object code your ADD NRS program is stored. When your data disk is in place, respond to the D1 prompt by typing type. All right, so did we write this down somewhere? We didn't write down how to do it. So let us write down how to do this in our gist. So we'll do edit.
Je sais pas.
So we'll write down how to execute program. We'll say auto start. What is this called? Self-starting? How did they title this? Self-booting program. So we'll say that. Self-booting programs. Here we go. We first have to load get a data disk with your program binary on it. So here is basically C OSA plus save object code program. Okay, so we need a data disk, and then we type e:/d1 startup.xc. This program is basically saying E, which is the keyboard input, I believe, and says take everything from the keyboard input and put it inside of startup.exe. And then it's going to take whatever you type from the keyboard, which you should type in D1 space type. Oh, no, that's not what that's just what it'll respond with. Then we're supposed to type in load add numbers.object, and then we type in run 0600, and then we press Control 3. And Control 3 will exit out of this mode of like copying everything you type into startup.exe. And then you type in check that startup.exe is in disk by typing dir. Okay, and then after that, let me see, what is this thing saying? I'll show it to you again. Then if the startup.exe file is there, you can check to see if it works by turning your computer off and then on again. When your computer is up and running, load your debugger and check the, then we can just check. So restart computer. Shift F5 on Altera. All right, so that is what we're supposed to do. You can see my finished browser gist help cheat file here. All of this should be in the eventual VOD. Is this kind of too big? What's going on here? Alright. So we get a data disk. This was a little hard for me because I don't know Atari DOS. And then we do this to create this file, which is basically just loading the object file and then running the stuff in memory. And then that's it. It's really easy. So let us first, this is the hard part, getting the data disk. So let's try to make a new data disk because this was kind of tricky. I think what we needed to do was basically learn how to copy a disk. You can use the duplicate copy command, dup disk. Alright, I think that's what we need. So let us do that.
Elle a pas fait de miracle, l'autre en mage blanc. Enfin, typiquement, claquer un miracle ou deux, ça t'immobilise tout le monde, ça te fait gagner du temps, quoi.
We need to find a full DOS disk. And to do that, let me actually share my full desktop so
Comme il
you
fallait.
can actually see how I'm doing this, because right now you won't see the menus I'm using.
Alors, je te demande un instant parce que je vais aller mettre du chauffage, faire un
Uh,
thé, faire chauffer le chat et prendre une couette.
Desktop, here we go.
Ah bah, ouais.
And in my desktop view, I should also add
Oh my God.
this chat, right?
T'as vu
Chat
ça?
is here somewhere. There we go.
Bon,
Whoa.
Et comme c'est le plus fort, bonne nuit.
Okay. So I need to find a disk that has the whole
fromage.
that this is the eject button. We don't want to click on that. I think we can save here, right? That'll save what we just changed, like we've added those two files on mem test. Now we need to load in a full disk. So you can see I have something called Mac 65 with DOS XL230. I think that's a full DOS disk. Let me check. So we're gonna put that into drive. And now when we type dir, yeah, you see there's a lot of files here. The thing I look for is menu. So there's menu.com here on the very top, and that means we can load the DOS menu system, which is kind of, kind of cool, but all of these things you can type with commands too. It used to be very popular to have like a number driven system to do things. So what am I doing now? So I have this file. So if you guys want that file, where did it come from? I think it came from, I think I probably have that in YouTube, don't I? Let's see. When I look at Atari, does it tell me where it is? For how long?
20 seconds.
Alright, I'm gonna turn off my camera for 20 seconds. Oh, that's not it. There we go. Okay, but we're still here. Emulator, assembler, book, cheat sheet. I wonder where that was. I guess I didn't put it in my cheat sheet, huh? Debug from Atari wiki page. Let's see. What was that file called? It was called Atari Mac 65 DOS XL. Mac 65 DOS XL. I swear that we had this listed somewhere. DOS XL 2.30. I didn't write this down somewhere. Looking for disk. Maybe it's in here. I know my previous video we kind of found it, but kind of, oh, here's, I think it's the same name. Yeah, it looks like the same name. Mac 65 with DOS. Yeah, that's it. We can try saving this. Let's just, we can kind of test it to make sure that it works. So I just typed that in and I found it under looking for Mac 65 disk with Bug 65. That's on Atari Age forums. And that would be in my downloads. So I'm going to copy this file and we're going to put it in our Atari page here. Well, it's going to have a copy name, right? Replace the file, compare, skip this file. Wait, how do I do this? We'll rename this one. Original, copy, and now we should have this one. This one is the new download. So here we go. We're going to load that drive here. Disk drives. Load. New download. Okay. And now when I look at it, you see it has all of this stuff. I think we can turn on our camera again. Hello everyone again. Alright, so that's how you find that thing. And now we want to duplicate it basically to make a bootable disk. And in there we had a thing we wrote where in our gist that said use dupe. It's called dupe disk. So I think I do it like this. Dupe disk. Source disk 1. I'm going to see if we can use the same destination disk. Maybe this works. Format disk, yes. What can go wrong? Put source disk in drive 1. When ready, hit 1. Put destination disk in drive 1. So we're going to change the disk now. And we're going to eject this one. And I think there's a way for us to make a new disk. Single density. We want single density, I think, if we're doing the 800XL. File system, it'll be unformatted. So here's a new disk. And now it's ready. Formatting disk. Put source disk in disk 1. Wow, so it's going to have to do this like many times. This is probably a bad way of doing it then. Test2. I don't know what to call it. So source disk, which means we got to put back in the new download. Oh my god, let's quit this. This is ridiculous. This is no way I'm going to do this. Okay, so I just reset the computer. What we'll do instead is under disk drive, we have the new download that we just have, right? And then in the second drive, we'll use D2. We will make a new disk, single density, all that stuff. And we run, yeah, here's our DOS disk. Now we do dupe disk. And we say we're going to copy from disk 1 to disk 2, format disk yes. Put source in 1, destination disk in 2. Yeah, we're good. Okay, copy same disk again? No. Alright, so now when I go to D2, I see that I have the same thing, right? So now we can save this. And we'll call it, what should we call it? We'll call it boot. Okay, so this is our boot disk. And now we need to load our program. So on drive 1, we're going to put in that disk that has our program, which was, I think we called it, well, all of these have it. We've done it before, but I saved it in original, right? So in here you see sample, no, where's our mem test? Where that's not the disk. Which one was it? New? No, that's the one we just did. Copy, no. Bug. Now I don't remember which one we were using. But the roots one, oh, Manus. Hats off to you for real. Assembly language I had in 5th semester electronics lab. It was all move, R0, R1, exchange, move. I found it really hard. Yeah, it's really, it's kind of interesting though. It's kind of like quaint. Feels nostalgic. Does that chat show up here? Ah, yeah, it does. I don't remember where I put my file. I have like no memory. Doesn't roots tell you? There's our add numbers. There's our source. Okay, so now when I go into, there's our object code 2 that we saved. This is not from the session, but you know, good enough, right? So now we want a self-booting disk, but we want to put that in our boot disk in D2. So in D2, this guy is definitely not self-booting. Following the instructions we had before, it says to, here we go, here's the instructions. We are supposed to do type E colon, instead of D1, we're going to do D2, because this is where we're putting our boot disk. Startup.exe. And now we're just going to type stuff that we want it to do. Load add numbers.object code, run 0600, and then we type control 3. That saves that file. So now when we go here, we should see startup.exe. That's our program. And now when we restart this, let's move this into D1. I don't know if it really matters, but I think you boot from D1. So here we go. We're going to eject this roots guy. Whoops. How do I eject? Oh, this is eject here. And then we're going to eject this guy. And then we're going to load boot here. That's the one we made. And now you can see, oh no, oh D1. So this is the one we have. Oh, the one thing we didn't do is copy the file over. Damn it. All right, let's copy the file over. So in D2, we're going to put the object file that was in roots. D2 colon, right? So here's the object file. We have to copy it onto that same drive because otherwise it can't do the load. And then we have a thing up here on how to copy. So we look under the DOS section, run, erase, bootable. Oh, we don't have something that says how to copy. Let's try copy. Damn it. All right, let's bust out the Dead Sea Scrolls. We did this last time. Be afraid. 1 second. That was this file, I think. Yeah, oh my god. Don't be too afraid. This is just a manual of Atari's DOS commands. I'm trying to see, where am I? No, I don't think this is it. I think it's back here somewhere. All right, we're in 5, we're in 4. 5. Section 5, intrinsic Excel commands. Directory, protect, erase, rename, load, save, type, DNS. Okay, so we must need an extrinsic command. That means it's something it loads. Okay, here's the extrinsic commands. Config, clear disk, copy. Didn't we try copy already? Source file to destination file. I thought we tried this. Copy. Ah, there we go. It's just because I was in D2 and D2 is not a full DOS disk. So D1 is, so you'll see that it has all of this. And look, there's the copy command. So copy, and we want to copy D2 add numbers dot object to D1 add numbers dot object, I think. And now when I look at this, I see add numbers dot object. Let's assume that object is correct. Now this should be a self-starting disk. Now we go into disk drives. We don't need this other disk anymore, just our boot disk that we made, which has DOS and the add numbers.object file, and it has the startup.exe file. I'm going to add a note in here which says that we should copy the object file. Copy the object file to the self-booting disk. There we go. This is copy extrinsic DOS command. Alright, so now when we restart with Shift F5, this should, you see it ran and our program, it loaded and ran our program. Oh, Alex Blue, sorry I didn't see. We are doing Atari 800XL 6502 assembly language programming. So, how long did I miss you? Oh, that was like just 3 minutes ago. We're going through this book, Atari Roots, and we are learning how to program an Atari 800XL using the Altera Atari emulator. Okay, so now if I run the debugger, which should be in here, right? Do we have the bug 65? We have Mac 60, we have bug 65. Let's try running that. And now I display memory address CB. And here we were adding 2 plus 2 rather than 10 plus 2. So it's showing 4 here. You'll have to take my word for it because we wrote that version of it in another on another day. All right, so that we have reviewed how to create a self-booting program on Atari. What is this? Oh, this is me making it huge. 1 second. All right, let's make this back to a normal, reasonable size. There we go. That's okay. And I think that's where we are now. Yep. So here we're going to start the next section after our nice review just now on calling machine language programs from BASIC. I think actually we read this and it said that we won't do this now. You can also run machine language programs by calling them from BASIC programs, but it's a complex process, so we'll basically do it in chapter 8, right? Oh, cool. So we're on chapter 6 now. let's try doing some of chapter 6. I don't know how far we'll get. Um, this is looks like it's going to be about how to choose the right address for, I guess, when you start your Atari program. Need some water. So for those of you who are just joining, we're doing Atari 6502 Assembly Language Programming. We've been reading this book, Atari Roots, that teaches you both about the 6502 CPU and also specific stuff to the Atari. So now we are going into this. We've covered a lot of ground the first 5 chapters of this book. Is this a little small? How do I make this bigger? Ah, well. Is that better? Let's see. I think that's easier to read for you guys, right? I think so. We've covered a lot of ground. Now you have a pretty good idea of how your computer works and you know what goes on inside your Atari 6502 chip when a program is running. You now know the principles of the binary and hexadecimal number systems, and you know how to write, debug, load, and save assembly language programs. Yes, we just did all of that, so that is true. But we've really just begun to explore the capabilities of the 6502 assembly language. The 6502 in your Atari computer is an incredibly versatile device. It has only 7 registers and it understands only 56 instructions. 56? So small. But with those limited facilities, it can do some amazing things. One reason the 6502 chip is so versatile is because it can access the memory locations in a computer in 13 different ways. What? It has 56 instructions, but it has 13 ways to address memory locations? Access? In other words, the 6502 processor has 13 different addressing modes. In the world of assembly language, an addressing mode is a technique for locating and using information stored in a computer's memory. In the programs presented in this book so far, we've used 3 addressing modes: implicit addressing, immediate addressing, and zero-page addressing. I remember implicit, I think that's when we do the $sign. Immediate addressing, I assume, well, actually, we'll see. In this chapter, we'll be examining all 3 of those addressing modes along with 10 others that are available. Wow. Every 6502 instruction must be using one of the addressing modes. Not one instruction is capable of using all of the addressing modes, and no addressing mode can be used by all of the instructions. The instruction tells the processor what to do, and the addressing mode tells the processor what to do with it. On the following page is a complete list of addressing modes and the format of the operation so you can tell what mode you are using. These formats are standard for the 6502 microchip, so they should be understood by most 6502 assemblers. Alright, so implicit, implied addressing mode, RTS. Okay, so RTS, there is no address really that we pass in. It's just saying go back. Accumulator, yep. I don't know ASL, but got it. It's just dealing with the accumulator, maybe. Immediate, we've done this, where we're just telling it directly put this number in there, into the accumulator. Absolute, load accumulator, we haven't done this with I assume like whatever's in this memory address. So look, load accumulator can take both, right? Zero page, store CB, okay. This is when we stored the result of the accumulator, store accumulator into this address. relative BCC label, absolute indexed X. So, okay, so this is probably using whatever's in the register X and maybe adding it to 5000. Absolute Y, 0 page X, 0 page Y. We haven't done any of these. Indexed, indirect, indirect, indexed. These are just opposite, right? Indirect. So let's take a look. The 3 instructions marked by asterisks are the ones we've used in this book so far. All 3 appear in addnumbers.source, the 8-bit edition program introduced a few chapters back, which we'll take another look at now. We're very familiar with this now. This is implied address. Because there's really, it looks like implied has, we don't actually pass anything, right? Clear carry, load number 2, load accumulator number 2, immediate. Add with carry number 2, immediate. Store address CB, 0 page address. Return subroutine, implied address. In this example, the 3 address modes used in the program are identified in the comments column. Let's look now at each of these 3 address modes, implicit or implied addressing, that we use for clear decimal mode, clear carry, and return subroutine. When you use implicit addressing, oh, here we go, Chuck, welcome back. It's good to hear from you again. ASL is arithmetic shift left. Shift all the bits left. Leftmost bit goes into the carry flag. Whoa, okay. The left is the most significant bit, I assume. How are you doing? Okay, where are we? When you use implicit addressing, all you have to do is type a 3-letter assembly language instruction. Implicit addressing does not require, in fact does not allow, the use of an operand, right? So none of these take any arguments. The instruction in an implied address is thus similar to an by the way, Chuck, I saw your Atom video. It was like 4 or 5 hours long. And I was always like, I always wanted to play with an Atom, but like everyone I knew hated Atom for whatever reason, but I just thought like, wow, it looks so cool. I want to like play with one. Never had a chance to. But now after watching like 4 hours of your video with every detail and every software, like I feel like I know it. And that was amazing. That was amazing. It was like, that's exactly what I wanted, you know? Anyway, thank you. When you use implicit addressing, yeah, we read this. In the instruction in an implied address is thus similar to an intransitive verb in English. It has no object. So it's like Alice runs, Alice cooks, or whatever, right? The address it refers to, if it refers to an address at all, is not specified but merely implied by the mnemonic itself. So no operand is required or allowed in the implicit addressing. Opcode mnemonics that can be used in implicit addressing mode are, and then they give us several. This is probably break, this is the clear carry, this is the decimal mode. Don't know these. Decrement X, decrement Y, increment X, increment Y, no op. Don't know what those are. Return subroutine. No. Okay. So out of the 56, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So almost like half of them basically are implicit addressing mode, which is interesting, right? Immediate addressing. When immediate addressing is used in assembly language instruction, the operand that follows the opcode mnemonic is a literal number, not the address of a memory location. So in a statement that uses immediate addressing, the number sign, hash, the symbol for a literal number, always appears in front of the operand. When an immediate address is used in an assembly language statement, the assembler does not have to peek into a memory location to find a value. Instead, the value itself is stuffed directly into the accumulator. Then whatever operation the statement calls for can be immediately performed. Instructions that can be used in the immediate addressing more are, we've seen add with carry, and compare, CPX, maybe compare X, compare Y, or is it copy? No, I don't know. EOR, LDA is load accumulator, LDX, LDY, assume that loads X and Y, or A, maybe it runs the OR, logical operation with A, SBC, subroutine something, don't know. Oh, like this is ugly. What's going on? Sorry, guys. That's better, right? It isn't difficult to distinguish between a statement. This is zero-page addressing. It isn't difficult to distinguish between a statement that uses immediate addressing and one that uses zero-page addressing. In a statement that uses zero-page addressing, the operand always consists of just 1 byte, a number ranging from 00 to FF, and the number equates to an address in a block of RAM called page 0. Oh, so when we stored it in CB, when we stored the accumulator in CB, that was page 0, that was zero-page addressing. Taking a quick look at what this is saying. Oh, my bit rate's too high, it says. Alright, back to this. Is something wrong? No? God, I don't see how we can get through 13 of these tonight. Okay, so here we go. The hash symbol is not used. The hash symbol is not used in zero-page addressing because the operand in a statement that always employs zero-page addressing is always a memory location, never a literal number. So the operation called for in the statement is performed on the contents of the specified memory location, not on the operand itself. Zero-page addresses use 1 byte operands because that's all they need. As we just said, the memory locations they refer to are in a block of your computer memory that's called, logically enough, page 0. And to address a memory location on page 0, a 1 byte operand is all that's necessary. So I wonder why it's limited to 1 byte. Probably because, like, so you have to it sounds like it means whenever you move something out of the accumulator, it has to always go to page 0. Maybe because it's just faster. Alright.
Did you change it? Did you change
No, why?
the login, the password?
Oh no. Specifically, the memory block in your computer known as page 0 extends from memory address hexadecimal 00 through memory address FF. You could just as easily and just as correctly say that page 0 extends 0000 to 00FF hexadecimal, but it isn't really necessary to use those extra pairs of zeros when you want to refer to zero-page address. When you follow an assembly language instruction with a 1 byte address, your computer knows that the address is on page 0. Since zero-page addresses use memory saving 1 byte operands, page 0 is the high rent district in your Atari's RAM. It's such a desirable piece of real estate, in fact, that the people who designed your computer took most of it themselves. Most of page 0 is used up by your computer's operating system and other essential routines, and not much space has been left there for user-written programs. Later on in this book, a chapter dedicated to memory management will discuss the memory space available on page 0 in more detail. For now, the most important fact to remember about page 0 is that it's an address mode that uses a memory address on page 0 as a 1-byte operand. Instructions that can be used with 0-page addressing are, we know, add with carry. Chuck told us about ASL, arithmetic shift left, bit, compare, copy X, copy Y, decrement, increment, load accumulator. So when you load the accumulator, I see. We used it with immediate mode last time, but you can also use it with 0-page addressing. Is that what it's called? Yeah, 0-page addressing. Load X, load Y, all of these. Store A. Yeah, that's what we did. We used page 0 addressing for store accumulator. Alright, new addressing modes. Now we'll describe 5 6502 address modes we haven't covered so far. Oh, these are kind of short. Accumulator addressing, format ASL, arithmetic shift left, A. The accumulator addressing mode is used to perform an operation on a value stored in the 6502 processor's accumulator. The command ASL-A, for example, is used to shift each bit in the accumulator by 1 bit position, with the leftmost bit, bit 7, dropping into the carry bit of the processor's status P register. Other instructions that can be used in the accumulator addressing mode are LSR, some shift right? I don't know. ROL and ROR. So, when you shift something to the left, I'm guessing it's basically multiplying it by 2. Alright. Absolute addressing, format STA $5000. So notice it's not two hexadecimal numbers, but 4. So this is not 0-page. Absolute addressing is similar to 0-page addressing. In a statement that uses absolute addressing, the operand is a memory location, not a literal number. The operation called for in an absolute address statement is always performed on the value stored in the specified memory location, not on the operand itself. The difference between absolute address and 0-page address is that absolute address does not have to be on page 0. It can be anywhere in free RAM. So an absolute address statement requires 2-byte operand, not a 1-byte operand, which is all that a 0-page address requires. This is what our add source program would look like, add numbers program would look like if absolute addressing instead of 0-page addressing were used. So here it's our same program, we're storing it here in the same place. And then here, instead of storing it into CB, we store the accumulator into memory address hexadecimal 5000. So it looks like store accumulator can be either page 0 or it could be absolute addressing. The only change that has been made in this program is the one in line 100. The operand in that line is now a 2-byte operand, and that change makes the program 1 byte longer. But now the address in line 100 no longer has to be on page 0. Now it can be the address of any free byte in RAM. Mnemonics that can be used in the absolute addressing mode are, and then we have some of them like add with carry, address shift, arithmetic shift left, compare, all of these ones, store, accumulator. Relative addressing, here we go, BCC next. How is everyone? How's this working?
Oh no.
What's the matter? Alright, looks like everything's working fine. Alright, we're now up to relative addressing. Another one of, so we've covered, what was the first one? The first one we had immediate addressing. We have implied addressing, right? Implied was something like RTS, which doesn't have an operand. Then we have immediate, which is like load accumulator number sign 2, which says just take this number immediately. And then we have page 0 addressing, which is when you have a 1 byte memory address. And then we have absolute addressing, which is absolute addressing, which is a 2 byte memory address. Alright, so now we're up to relative addressing. Relative addressing is an address mode used for a technique called conditional branching, a method for instructing a program to jump to a given routine under a certain specific condition. There are 8 conditional branching instructions or relative address mnemonics in 6502 assembly language. All 8 begin with B. So the BCC is branch. B, which stands for branch to. Examples of the conditional branching instructions that use relative addressing are BCC, branch to a specific address if the carry flag is clear. BCS, branch to a specific address if the carry flag is set. Okay, now we got like if statements, right? This is cool. BEQ, branch to a specific address if the 0 flag is set. How is zero flag EQ, right? That's going to be hard to remember. BNE, branch to a specific address if the 0 flag is clear. I see, because probably you do a compare right before, and compare is probably going to compare 2 things, and if they're equal, they'll be, the difference between the 2 numbers are going to be 0, and then so the 0 flag is going to be set. That's probably why this is basically saying it this way. It's equal because the 0 flag is set. All 8 of the conditional branching instructions will be described later on in this book in a chapter devoted to looping and branching. I wanted to do looping and branching sooner. Alright. What comparison instructions do? Let's see, we're on page 99. Let me see how much further we got here. Indirect addressing. A rarely used mode. That sounds really spooky. LIFO. Okay, maybe what we can do is get to how 6502 uses the stack, and that'll be a good stopping point. Oh, we're so close. 106 is the end. Alright, let's see if we can get there. Alright, let's see. What comparison instructions do? The 8 conditional branching mnemonics are often used with the 3 other instructions called comparison instructions. My New York accent's called. Typically, a comparison instruction is used to compare 2 values with each other, and a conditional branch instruction is then used to determine what should be done if the comparison turns out in a certain way. The 3 comparison instructions are CMP, compare the number in the accumulator with, CPX, compare the value in the X register with, and CPY, compare the value in the Y register with. Conditional branching instructions can also follow arithmetic or logical operations and various kinds of tests of bits and bytes. Usually a branch instruction causes a program to branch off to a specified address if certain conditions are met or not met. a branch might be made, for example, if one number is larger than another, if two numbers are equal, or if a certain operation results in a positive, negative, or zero value. An example of conditional branching. Here's an example of an assembly language routine that uses conditional branching. Okay, let's see. This is exciting. We got our second assembly language program. So we have the same thing where we're telling it that we are starting our program in memory address 0600. This is a assembler directive and not an opcode. Add 8 BTS. This is a label. We're clearing the decimal flag, the decimal mode flag, or whatever it's called. Now we're clearing the carry flag. We're loading the accumulator with, so now we have a memory address, right? So it's saying load the accumulator with whatever is in memory address 5000. Then we're going to add with carry. So this is going to take the whatever was loaded and add it with whatever was in memory address, is in memory address 5001. This is absolute memory addressing. BCS error. Branch if CS. Branch if carry flag is set. Okay, so when it adds it, it wants to know if it's bigger than 256, and if it's bigger than 255, and it's bigger than 255, we branch to error, which basically returns from this thing, the program returned from subroutine. And then I guess if this isn't the case, if the carry flag isn't set, it just continues. So now it's going to store the accumulator value into address, absolute address 5002, and then return. This is an 8-bit addition program with a simple error checking utility built in. It adds two 8-bit values using absolute addressing. If this calculation results in a 16-bit value, a number larger than 255, there will be an overflow error in addition, and the carry bit of the processor status register will be set. If the carry bit is not set, then the sum of the values in 5000 and 5001 will be stored in 5002. If the carry bit is set, however, the condition will be detected in line 100, and the program will branch to line labeled error. This is a label because you see it's one space earlier than everything else. That means it's interpreted as a label. At line 100, you could begin any kind of routine you wanted to. You might choose, for example, to write a routine that would print an error message on the screen. In this sample program, however, an error results only in an RTS instruction. The only problem with this is that we can't really test it because stuff in memory address 5000 is going to be 0. So it's just going to add zeros, right? But what we could do is actually write a program that stores stuff in those values. Do you want to do that? And we can see if we actually know what the heck we're doing. So let us use Max65. Well, maybe we can just use this version. And we're going to write this program. So the only difference is that we need to add an extra directive for the Max65 called opt_obj, which tells it to store the program after assembly into memory directly. Now we're going to say that's where our program starts. Put our program there. Then I'm just copying the stuff that's important. Add 8 bits. 8 bits. CLD. Clear carry flag. Load accumulator with... Okay, so the difference here is that we can't load the accumulator with 5,000, right? What we have to do before that is probably like store something in the accumulator into address 5,000. And I know that we can do this by loading the accumulator with the number, let's say, we did 2 before, right? And then we can do like store the accumulator into address 5,000. Right? Let's also load the number 5 into the accumulator now. And then we'll save that into 5001. Now, so in 5000 we should have the number 2, and in 5001 we should have the number 5. Okay, so now we're going to do the normal program, which is going to load the accumulator with our number 2 again, right? And then it's going to add with carry whatever is in 5001, which should be a 5. So it should have a 7 in the accumulator now. And then in line number 100, we say branch if the carry set flag is set to error. Otherwise, store the accumulator value, which is 7, into 5002. And then return from subroutine 130. This is a label. I'm going to put one space only. Error. Return from subroutine. So here's our assembled code. We have to remember that the last instruction is in 0618, right? I should write that down so I don't forget. Last instruction is 0618. So we're starting in 0600 to 0618. And now, I guess we might as well save this onto disk, right? So we'll do, no, it's called list. I always forget. It's so tricky. We'll call this like add8.source. I'll write this down too because I forget everything. So this should save it onto our disk. Now we should be able to go back into DOS. And now I'm going to run bug65. And now I'm going to display some things in different addresses. First of all, if I look at our code, you see that we have code here, right? That's our code. And then if we display 5000, it's empty. So this is 5000, 5001, 5002, whatever. It's all empty. So that's good, right? Now I'm going to tell it to run our program, and I think that was like 0600 at 0618 to say where it ends. Oh my god, it failed. Let's restart. Sometimes this happens. Maybe because we have like this auto starting program. Let's try it one more time. How do we load stuff? It's called enter, right? There's our program. We assemble it. We can run out. Sometimes the second time it runs, it's fine. I don't know why. Now we do go 0600 to 0618. No, it's not happy. You don't see this, right? Here, this is what it looks like. I get this little pop-up menu. So why is it failing? Last time it failed, it was because my system was loading BASIC by default. Let's see, where was that? That's under system configure. BASIC, enable BASIC. No, that's not what we're doing. Maybe it's actually the version of Max 65. Let's load the one that I was using before. I think that was here. And then on the second drive, we will have the boot. Okay. Yeah, so here we're restarting. Then we run Max 65 420. Maybe this version, it's the same version, it should be the same, right? Enter, now we're on drive 2, and it was called add 8.source. We can list it, now we can assemble it. Maybe my program's just bad, maybe that's why. Maybe I don't know what I'm doing, you know? Cheap viewers, okay, this is not cool. Alright. Okay, so now I compiled it. Now I go back into DOS mode, and now I should be able to run Bug 65. Maybe this version is different. So now I do G0600 at 0618. No, it fails also. We have one last thing we can do, which is let us use the DOS run command instead. 420, enter D2, add 8.source, ASM, CP, run, right? Run 0600. That didn't crash. Bug 65. And I'm going to display where we're storing in 5000. There we go, look at that. It stored, the first thing had the number 2, remember, because our program was storing the number 2 into address 5000. Then we stored the number 5 into 5001. We add the 2 together and we store that into 5002. So here's 7. So, you know, we got there eventually. I don't know why it's acting buggy, but you know, some people have told me that like these programs are using some of the memory that we're trying to use, and that's why it kind of fails. So we have to kind of learn how we need to choose memory correctly. But we know that it works, so that's good. We validated that we are learning indeed what we are learning. But it means we're going slower than we thought. We were hoping. Does that make sense to everyone? How much of this are you guys following? Where were we? This is an 8-bit program with simple error checking built in. We did this. Yeah, okay. We read that. Absolute indexed addressing. LDA. An indexed address, like a relative address, is calculated by using an offset, but in an indexed address, the offset is determined by the current content of the 6502's X register or Y register. A statement containing an indexed address can be written using either of these formats: load accumulator absolute address 5000 comma X, or load accumulator absolute address 5000 comma Y. How absolute indexed addressing works? Is that what it's called? Absolute indexed addressing, right? This is probably how you do like a for loop. If you want to like iterate through a list of elements, then you just have like the X basically increment by 1, and it keeps like going through to the next memory location. Why is the browser a little scuffed again? Kind of weird, right? When indexed addressing is used in an assembly language statement, the contents of either the X register or the Y register, depending on which index register is being used, are added to the address given in the instruction to determine the final address. Here's an example of a routine that makes use of indexed addressing. The routine is designed to move byte by byte through a string of ATASCII, Atari ASCII characters, storing the string in a text buffer. Oh, this is cool. When the string has been stored in the buffer, the routine will end. The text to be moved is labeled text, and the buffer to be filled with the text is labeled text buff. The starting address of text buff and the ATASCII code number for the character return are defined in a symbol table that precedes the program. All right, let's try to understand this. This is cool. So text buff is 5000. This is where we want it to go to, our destination. End of line is 9B hexadecimal. What? We'll see. This is the start of the program, and here is text. I guess this is just, I don't know what this is, but I assume this is our text that we want it to be. This is like a string. Data move. This is a, oh, this is a label. Because it's only one line, right? One line. Yeah, one line. So this is a label text. That I understand. Since it starts with a byte here, this must be a assembler directive. So this isn't actually an opcode. So this must just be something the assembler just probably like makes an array of bytes. Data move is a label. Load X 0. So the X, what is it called? Register is, we set it to 0. We initialize it to 0. I'm finding my English words are getting hard to find. So loop is a label, and it starts with a load accumulator text offset with X. So probably it's going to get whatever this is, the first one, 54. And it's going to store into text buff this basically this variable, this constant. It's going to store at this absolute address 5000, but we're going to increment it by X. So this is now the absolute indexed address. So X is 0 at first, so it'll just be 5000. Compare end of line. So it's going to check if it's the same as EOL. EOL is 9B, and this is 9B. So I guess this is like representing the end. So it's checking if we've reached this character. CMP, compare whatever's in the accumulator, I'm guessing. Let's go back up. CMP, compare the number in the accumulator with. Yep. So that means it's just because we loaded it into the accumulator, we can check if whatever's in the accumulator, see if it's the same with EOL. And if it is the same, the zero flag is going to be set so it's equal, and then we go to fini. So fini just means return from subroutine and end. Maybe in my program I forgot to write an end. Is that right? That's how you load, right? I forgot an end. It's still 1618, but maybe that makes a difference. So now I'm kind of curious if bug 65 will actually run now. Nope, that wasn't it. Oh well. Qu'est-ce que tu fais? Oh yeah, take it then. It's fine. We're fighting over USB cables. Alright, so where were we here? Compare if it is the same, then go to end, fini, where we return from subroutine and go end, and then otherwise we increment x. So this is incrementing the x register, which we set at 0 at first, and then we're going to jump to loop. So here we go back to loop, and we just keep doing that until it eventually breaks out when this branch when equal is met. So here we have, should we try to write this? There's no way we're going to finish then. Maybe we write this and then we stop for today. Alright, should we try to write this without looking at it? No, we're going to have to copy the bytes. No, we're not. We don't have to copy the bytes. We'll just cheat a little bit. We'll glance at it every so often while we write this, okay? Alright, so let's go back to Max65. Hello, GSN. This is new nostalgia for me. Is that Atari? We're learning assembly on an Atari 800 XL emulator. And it is emulating an Atari 800 XL. So we've been doing this as a series of, there's a whole bunch of YouTube videos. I don't know how far along we are. If you look at my profile, you should be able to find it. And we are at, we're doing this book called Atari Roots, where there's a browser version of this you can kind of find. Where is it? Here? Where are we? Here's the browser. And we went through the introduction. We learned about bits, bytes, and binary, then the 6502 registers and stuff like that. And then we learned how to do basic, an assembly language program that just adds 2 numbers. And then we learned how to run it. And we also learned how to make a self-booting disk. So that was kind of cool, where you make an assembly language program and then you boot your Atari and it just runs. And now we're on chapter 5 or 6. No, we're on chapter 6 now, so we're getting pretty far. Well, how far? How far is chapter 6? Yeah, we still got a bit to go, right? But we're doing okay. So that's why. Are you? Do you have have you had an Atari? Is that something you're familiar with? Happy holidays. Keep up the grind of low-level programming. I will. All right. What happened to my Atari roots? There we go. Somehow I lost it. All right. So let's try to write this without looking at it too much. I'll just put it off my screen a little bit. So we'll do a new, and so we have nothing here, right? And we kind of know we got to start with stuff like option to load the object code into memory as soon as it compiles. We know that like we want to tell it the starting address of the code. I think I need the $sign. Let me check. Yeah. We're going to use page 6 of memory for that. And now we can start the code. We need the text stuff. I won't, this I'll just copy mostly. So text is a label. Byte, I don't know how this works, but we'll give it a few bytes. We won't give it as many, so we'll copy a few of these. And then we'll just assume it ends here. $9b, right? Because 9b is the end. And now I will just try to write it on my own. What? What was the first thing it needed to do? God, writing this stuff is hard. We know that we have to, oh shit. We know that we have to clear, let's clear the decimal mode. And we're going to clear the carry flag. It just seems like this is good stuff to do. I'm sure that's not how they did it. And now we want to probably set the X register to 0, right? So how is that? That's called like load X maybe? I'm just guessing here with 0. Let's see if this fails. Okay. Now I think I am set to like loop. So I need to create like a loop label, right? Oh, I never set where I want this to be copied to. So I need to have that line. Let's make that line 110. And it was like text buff, right? Or something like that. I have to cheat because I don't remember the syntax for this. Text. This is a label, right? Just one line. Yeah. Text buff is equal to 5,000. And we have end of line is equal to $9b, right? So let's look at this in order here. We have compiler directives. Then we have a label like this. Text buff is equal to this. End of line is equal to this. So now I'm going to make like a loop command, I guess. A loop label. And in here, we're going to load the accumulator with text. No. Right, yeah, it's text. It's whatever is in text, comma, X. Is that right? So this is the indexing. We're trying to get stuff from this text thing and index through using X. Nope, that's not it. Oh, it's probably not. It's probably just text. Because text itself is probably an address? I don't know. Let's try this. Hey, that worked. And then after this, we're going to load. We copied it there. Do we need to increment? No, we don't increment X now. Now we want to store that. Store the accumulator into, did I put 2 in here? I think so, yeah. store the accumulator into text buff comma x, right? So this is absolute indexed. So it's going to increment it. And then after this, we want to compare. So we want to compare what's in the accumulator with the end of line, right? And now we want to branch if it's 0, which means it's equal to the end of line. We want to branch to fini. Otherwise, we want to increment x. I'm guessing we just pass an immediate value of 1. Or maybe increment x is implied and it doesn't take anything. Let's see. Maybe you can only increment by 1. And now, we just go back, right? Jump to loop. And then, hello dude, what's up? I'm one of your fan here. Kindly add me on Discord. You can, I have in my bio my Discord server. You can just join and I will gladly chat with you there. So there you go. Thanks for joining. Okay, so we just jumped. I probably am really screwing up, right? Ah. Well, let's see what happens when if I didn't know, and like let's see what happens. How do I say this, Joaquin? Let's see what the assembler does. Oh, it probably will try to treat it as an address, right? That's bad. Yeah, let's do that. Let's not give ourselves. No, I want to see what it will do. So we will add 195. What is it? Rem? No, it's semicolon. Remove. Use. That way, at least we won't forget. Okay, jump to loop, and now we want to, if it doesn't jump, 240 is basically we needed to give this one as the end, and in the end, we're done, right? So I think we just do RTS, and 250, we do dot end. All right, let's see how off I was. Text buff equals 5,000. I don't think the order matters here. 5,000, yes. EUL equals $9B. Then we have the code starting at page 6. I'm guessing none of this ordering matters here. Then we have the text. Oh, yeah. So we have longer text. Then they have a label called dat move, but I don't think this is never used. So this is never used. So this dat move doesn't matter. Then we have LDX 0. So these things don't matter. The clear decimal mode, 9B address. Wait, is that something from before? Oh. Ah! Yeah, that's right. Yeah, 9B address. I get what you're saying. Yeah, it's not a 9B address. Okay, LDX0, that's correct. Loop, yes. LDA text comma X. Hey, I'm feeling good about myself. Store text buff X. Hey, even better. Okay, compare AOL EOL. That's a mistake. This is bad. This would probably try to compare something with whatever's in this address with what's in the accumulator, and who knows what's in 9B. Then we have BEQ, fini, yes. INX to increment the X. Look, I was right. It didn't take any parameters, so that is an implied addressing mode. Jump loop, fini, RTS, end. Hey, that's really not bad. So let's save this broken program. Enter. What was this called? I don't know, dat move dot source. Whoa, whoa, whoa. Oh, thank God. Oh my God. Enter just seems like saving to me, but thank God that program doesn't exist. Oh my God, I almost lost that. That's so scary. I wonder how many people have done that. Okay, list will, yeah, list is print, so this is how you save something. There we go. So now we have dat_move.source. I should probably write that down because I forget everything. Let's see if it assembles. It did assemble, but we know it's bad, so let me fix that. All right, C99B. C9 must be the, C9 is the opcode for compare, and 9B is the value we're comparing to. Whereas before, I wish I could see it before. Let me actually, I'm kind of curious how it looks differently. So if I had that before, it was 200 compare EOL, right? And now you see it over here, compare EOL C5 9B. Is C5 different here, isn't it? It wasn't C5 before. C5. C5. Let's remember C5. Yeah. Now it's C9. So even though the opcode that we're using is the same, the actual machine language opcode or whatever it's called is actually different. So there's a different CMP for the different addressing modes. So that's interesting to know. All right, so now we have our code. Let us try running it. So I think that means I can just run 0600, right? It runs. And now when I try to display 5000, I should see stuff. And it has the number 54, 41, 4B, 9B, because I gave up, right? Which means TAC. I'm sure that if we kept going, do we want to know what the rest of it says? Maybe we want to know what the rest of it says, huh? Maybe they tell us here. Let's try to cheat and see if they tell us. No, they don't tell us. We'll never know unless we type it in. All right, we're going to type it in. Enter is loading, right? Yes. All right, let's actually finish the text. So we have 54, 41, 4B, 45, 20, 4D, 45, 20, 54, 4F, 20, 59, 4F, 55, 52, 20, and our last line 4C, 45, 41, 44, 45, 52, 21, 9B. There we go. And now we can save this. List, remember? Maybe dot move 1. Alright. And now we can exit. And now we can run 0600. And now we can run our bugger. Oh crap, what? What happened? What I do wrong? Here's the text 414B da la 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 la. That's all right. 9B's at the end. Here. So why would this be confusing? 0 errors. Run 0600. Oh crap. Something's not happy. Zero 0102 text buff 9B. Use end of line. Oh look, I screwed up again. We ended up comparing with end of line like this. So now we can assemble this and it should be C9 here or something. Yeah, C9. And now we should resave this. That is print. Print is list. Okay. Now we go here, we run 0600. Oh, come on. Did I recompile after that? Maybe I didn't. What am I doing? This has 9B here. AOL equals 9B. Use EOL. Yeah, we did that. This should run. Compiles with no problems. I think maybe it's because we did multiple lines here, but I think I did this right. And now I should be able to go back here. Run 0600. No. That is unfortunate. Let's try to make it shorter and just see when it starts to crash. So we're just trying, we knew that when we had the one line, remember it worked, right? Let me make sure, am I copying 54, 41, 4B, 45, 20, 4D, 45, 20. Then we have byte 54, 4F, 20, 59, 4F, 59, 52, 20, byte 4C, 45, 41, 44, 45, 52, 21, 9B. That all looks correct, and we have load 0. Store X, compare, finish, increment X, jump, loop, RTS. So it's really the same thing. All right, so let us, we didn't change anything here. So let us edit line 101. We'll just get rid of this. And we'll also get rid of line 1012. So we have this, and you can also see that now we don't have a 9B, so let's add a 9B. Maybe, whoops. We'll just put it in 1. Byte, $9B. Let's see if this fails. And now we can go back to DOS mode. We can run the code, and it fails. It said 170 not found. Why is that? Did you see that? Like briefly, it said that on the screen. Uh, 170 LDX 0 loop. No, that should be right. So our last program was something really short. It was, remember, it was byte 54, 41, 4B, 45. Let me add just a few more here. 20, 4D, 45. Instead of 20, we'll put a 9B. And then we'll get rid of 101, and we'll get rid of 102. So we just have one line now, like kind of like before, and see if this works. Yeah, this looks correct. Okay. Go into this mode and let's see if this works. Now even this version's breaking. Wonder why. I almost feel like I must be doing something wrong. Actually, let's load our second version. I mean, first, what is it? Dat move 1 still had the extra stuff, right? Error 170 file not found. Whoa, right, not D2. Yeah, this one has everything. Um, okay, this one has this, but we have an error in line 200 where we need to compare with EOL. Now, this is the program we had before that actually worked, so let's see what's going on. Right, this is the one that worked. EOL, fini, loop, text, text buff. Yeah, that all looks right. Oh, now this one works. Look at that. Isn't that weird? Yeah, so it has these 1, 2, 3, 4 numbers, right? So somehow when we added more, it failed. Well, I don't know why that could be, but I think we won't solve it today. Let's read what this says. When the program begins, oh, we're a little bit screwed here. One sec. All right. When the program begins, we know that the string ends with a carriage return 9b, as strings often do in Atari programs. As the program proceeds through the string, it tests each character to see whether it is a carriage return or not. If the character is not a carriage return, the program moves on to the next character. If the character is a carriage return, that means there are no more characters in the string and the routine ends. Yeah, that's how it should have worked, right? The other thing we could try is like changing the order of these things. Like maybe some of this ordering matters, but I can't imagine. I think when we learn more about what this means, the dot byte, maybe we'll come back to this and debug it, because the problem is we don't know what this dot byte means. Okay, we can do these two more. Zero page X addressing. This sounds really easy. Zero page X addressing is used just like absolute indexed X addressing. However, the address used in the zero page X addressing mode must, logically enough, be located on page 0. Instructions that can be used in the zero page X addressing mode are these things: add with carry, compare, increment. Yeah. Zero page Y is pretty much the same thing, except it can only be used with two mnemonics, load X and store X. If it weren't for the zero page Y addressing mode, it wouldn't be possible to use absolute index addressing with the instructions load X and store X. That's the only reason that this addressing mode exists at all. Alright, so next time we start, we'll do indirect addressing, and we will finish the chapter. So thanks for that. Sorry for like getting a little stuck on that. Why does this always do this weird thing? I think that's all. So hopefully I think that's all we got. So if you're watching this on a VOD and not on stream, then and you enjoyed this, please do like and subscribe. There's a Discord server you can join in the description or in my bio. What else do I usually say? I think that's it. So I also do videos on some other things like Nix which, if you don't know about, is a packaging manager and also a Linux distribution. We should do some COBOL videos soon. We're doing Rust. We did one Godot game engine video. We did some Gleam programming. So we got a few things to play around with. Thanks for hanging out with me, and I will see you all later. Thanks so much. This thing killed me. Like, I don't know why it didn't want to be helpful. And it just like kept crashing. You know, like maybe because we have a startup.exe. Okay, now we don't have a startup.exe. Now we run this. Yeah, because if we had the startup.exe, it's gonna load that other program and run it. So now if I run Mac 6520 and I try to load yeah, we assemble it. Go back here. No, it's failing. The other thing we can try is running the thing in the debugger. Oh, I should keep track of where it actually compiled to. Compiles to line number 62A. Just about. No, that failed also. Disk routines? Maybe something in 6000 is actually occupied. I guess there's a point there. How can I do this? I have a cartridge. I think I have a cartridge of this. But then I wouldn't be able to load the program. Maybe I can? Yeah, I can, right? Let's try this. I think Where's the cartridges? Here it is. Attach cartridge. And I think it's in here. Max 65. Here's the ROM. Okay, so we're in a cartridge version now. And I think, here, let me see. Okay. Can I still access the drive? Yeah, I can. Alright, let's see if this changes anything. Yeah, we'll look at 600. So how do I quit out of this? This is a cartridge version, and I have like, this DOS doesn't have, oh, it does have, I do have bug 65. That one's not happy. Debug 600, so we can just run 600 here. G command from ASM editor. You can? So you're saying I can just run it from here? Let me do that. So I load it. And now you're saying I can assemble it and I can just do, can I look at memory from here? No, right? No. But I can run it like this. And maybe, do I need to give it anything else? No, it didn't like that. I assume it's not the same. Nope. Sometimes when I exit and run the bug 65 a second time it works. Maybe I should try running these bug 65 v4. Maybe it's, what is this? Nope. Doesn't seem to work well with the cartridge. Oh, just bug? Bug, 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 bug. What do you mean, bug? Command bug to call the debug. But I did that. In Max 64, you mean, right? Max 65. See, I ran bug, nothing happens. I think it has DDT. You see this? But I don't know how to use DDT. Maybe it's like display 600. No, display. I don't know how to do things. But we can see this is our kind of program, right? No, maybe not. Yeah, you probably have a point. Maybe we're overriding something when we get too big in memory address 6000, right? So, for example, how do I detach? So probably when we're doing this, here we can like do bug 65 without anything, right? And then we can display. And you can see that it's all good, right? 1, 2, 3, 4, 5, 6, 7, 8. looks like it's all empty. Hey, S Sadam Dev. Yeah, we can't figure out why. We're at the end of the stream, but we're just trying to figure out why when we made the string longer, the assembly program failed. But anyway, I think we'll learn that when we finally get to, like, what's in different memory stuff and whatever. Oh, here's stack add. Interesting. All right, all. So yeah, there was. You can, if you want to see the previous videos on this Atari 8-bit assembly language programming, look at my bio, and you'll see links to YouTube. And one of my playlists has all these Atari videos. So hope you enjoy it, and I